Okay, so the plan for today, the agenda for today is to kind of recap what we have already seen in terms of iterative algorithms. Right, we looked at two types of iterative algorithm. One is called message passing. The other is also called message passing, but it has the belief aspect kind of added to it. The first message passing algorithm is not operating on beliefs as much as just the hard decisions, the bits itself, zeros and ones. So it is literally passing messages which are zeros and ones, or sometimes erasers if it is binary eraser channel. Then later on we saw that possibly the performance can be improved if we do passing of the messages in terms of beliefs. So although we have, I think, touched upon all the major points, what I realized is that there were certain missing parts. If you actually just look at my slides and try to implement the algorithm, you will have some questions that may not be directly answered from this slide. So I have tried to add some additional details to my slides, which I hope will make the algorithm description complete. So that is the objective of the first part of the lecture session today, where we are just pretty much going to just kind of review and recap what we have already seen. Okay, so the other thing that I wanted to emphasize is that, remember I told you that in the project that you will start working on, starting from next week, you have to do 4 different algorithms. The hard decision algorithm for the Ldpc codes, operating over binary eraser channel. Then soft decision algorithm for Ldpc code operating over the same binary eraser channel. And then you would do similarly hard decision for binary symmetric channel, soft decision for binary symmetric channel. So you will be working on 4 different algorithms. But what I wanted to re-emphasize today is that although it may seem like you will be developing 4 algorithms, once you develop the main message passing structure, then going from binary eraser channel to binary symmetric channel is going to be very, very simple, very straightforward. And that is what I hope I will be able to emphasize today. Okay, so this slide we have already seen earlier. This is also just a matrix vector product representation of the any type of linear block code. All that it says that if C is a valid code word, if C is generated using the generator matrix, multiplying the message vector with the generator matrix, then it is guaranteed that when you multiply H with C, then you're going to get all zeros. And the way to think of that is each individual bit that comes out, all these 5 zeros in this case, for this is by the way example for the 9-4 product code, all these 5 zeros can be thought of as forming a supervisory check node. And the purpose of that check node is to make sure that the parity check equations are satisfied for that particular row of H matrix. So we considered this bipartite graph implementation of that same equation. And we see that there is always going to be total of n minus k, which we are going to call capital U check nodes. This is equal to the number of parities introduced by the code. And then there are going to be total of capital N variable loops. And the reason why this is called a bipartite graph is because the check nodes are never connected with themselves. So there is no connection between the check nodes. Similarly, there is no connection between the variable nodes. So although the graph itself has total of, in this case, 14 nodes, they form two partitions. That's why I have drawn these 5 codes as squares and the other 9 as circles. Because the graph can be partitioned into 2 sets of nodes, that is why it is called the bipartite graph. And then we have defined the degree of any node as the number of edges that are connected to it. So the degree of check node here is 3. And the degree of a variable node is 2. And it's denoted as dc and dv. Okay, so that is what this graph shows, that each check node is connected to 3 variable nodes, and each variable node is connected to dv equal to 2 check nodes. And we can see that from this matrix also. So dc, which is the degree of a check node, and by the way, check node is each of these zeros actually. So you can see that dc is the column weight. dc is the Hamming weight of a column. So you see each of these columns have a Hamming weight of 3. And that same way, sorry, what am I saying? It is the Hamming weight of a row. Hamming weight of a row. So if you look at any row, the weight of that row is the degree of check node for that particular check node. And dv is the Hamming weight of a column. And so you can see that each of the columns have a Hamming weight of 2, and that is seen here, where each of the variable nodes is connected to 2 check nodes. And I think as I believe it was Vandan who rightfully had pointed out that there is a mistake in this graph. You see C4 has the dv value of 3 because there are 3 connections. That doesn't match with the 4th column, which has only 2 connections. So what we need to do here is, I believe we have to, this part here, this line is wrong. So this has to be struck out. So that has to be erased. And then we have to add a new line which connects S4 to C5, because C5 has a degree of only 1, and that also is not correct. So this was a mistake in this diagram. Okay, so moving forward, let us see the overall algorithm. This I think I had written in a little bit incomplete manner, so I have kind of rewritten this part. So first of all, we will set an iteration index that we denoted yesterday as t. So when we start out, obviously the iteration index is 0. And then we would load each variable node with the observed bits, or in case of binary eraser channel, there may be certain erasers. So we'll just load each variable node with the bits or the erasers at the output of the channel. And then how do we do the message passing from ith VN to jth CN? That we are going to describe in step 3. Now this part was missing earlier. So in step 3, in addition to calculating the message from VN to CN, we would also calculate the estimated code word bit or the ith VN. Okay. So that is, there's some detail that was missing that I have tried to add here. Then we will do message passing from jth CN to ith VN, and that is also described later on. And then step 5 is implementing what we called yesterday as the stopping criteria. And in this case, the stopping criteria is whether all the erasers are unerased, or if there are no changes happening from one iteration to the next, or if the number of iteration has exceeded some maximum number that you have set up. And this is completely the algorithm designer's decision. Some designer, some algorithm developer might say that I want the maximum iteration to be only 10. Some may want to make it 50. So this Tmax is a kind of an ad hoc number. And so if the stopping criterion is met, then we just stop here and we say that the estimated code word that we have estimated in step 3 at tth iteration, the last iteration, is my decoded code word. On the other hand, if the criterion is not met, then we increment the iteration index. We change t to t plus 1, and then we go to step 3 and then repeat. So 3, 4, 5 are kind of looped. Okay. Now, this also I mentioned yesterday, but here I have put it on a separate slide, that the main work here is in terms of implementing the Ternary Graph connections. So what do I mean by Ternary Graph? So the algorithm is to visit each variable node, meaning it has to visit each column of that H matrix one by one. And remember, H matrix has n columns, so it has to go to each column that it has to do sequentially. That part is not hard, that you can just put it in a for loop. But then it has to determine for each column what are all the check nodes that are connected to this variable. And I'll give you an example of this H matrix. So when it goes to column number 1, it has to understand that, okay, check node number 1 and check node number 3 are connected to me. And so I have to do message passing across these two check nodes, 1 and 3. When it is done with the first variable node, it goes to the second variable node, which is the second column. And then it has to realize that I have to do message passing across check node 1 and check node 4. And so on. That is what I mean by Ternary Graph implementation. So I'll ask this, when the algorithm reaches variable node number 6, who can tell me what are the check nodes that it has to do the message passing with? This column over here. That is the right answer. It is 2 and 5. Check node number 2, second row, and check node number 5, fifth row. So that is uh, the main challenge, basically, to kind of keep track of what are the check nodes that are connected to that particular variable node. And then it has to compute the message and pass the message. But that part is kind of just mathematical equations. The calculation of the message is not terribly difficult to implement, but it is keeping track of these connections, which is the main programming work. So that is the first thing that the algorithm does. So I would say this will be step 3.1. And in step 3.2, it will also calculate the estimate of the coded bit, Ci hat, for the ith bit of the decoded code word. And so how it does that is what we are going to look at today. So after it went over each column, now it has to do step 4, which is essentially visiting each CN, but that is same as going over each row of the parity check matrix. And so now it has to compute all the VNs that are connected to a CN. And the way it would do that is, again, if you go to this H matrix, for the first check node, it will say that I have to do message passing with VN1, 2, and 3. When it goes to the second check node, it will say that I have to do the second node, second CN is connected to VN 4, 5, and 6. So on. So this the set of VNs that are connected to a particular check node J, where J goes from 1 to number of rows of the H matrix, is decided by the locations of ones in that particular row of H matrix. And then in step 4, there is no 4.1, 4.2. Okay, in step 4, you just calculate the message and then just pass it to that particular variable. And so what you will realize is that this part here, step 3 and step 4, is purely software. There is no math here. You can write this in C++, you can write it in Java, you can write it in any language. There is no signals, there is no kind of fancy processing going on, there is no Fourier transform that we are taking, nothing. So it can be, you don't really need MATLAB or Python, because those languages actually allow you to do some matrix computations and algebra in an easier way. Whereas this is nothing, it's all pure software. So this part of the project, the Ternary Graph implementation, should be done by those of you who like software programming. Right? So in your group of 10 students, some of you may be feeling very good about programming algorithm. So they can take up this challenge. Okay, moving forward. This is what we have already seen earlier, so I'm not going to spend too much time on it. It's basically how the message gets passed, how the message gets calculated for the VN to CN. But this is a new slide that I added just to make it kind of consistent with what we saw yesterday in terms of soft decision decoding. And so I thought that I will add a very similar diagram for hard decision decoding, just to show you that, that Ternary Graph implementation, that software development remains the same. What changes is, what are the values that are passed over these edges? Now, for the hard decision decoding, the messages are denoted like this: BIJT and B hat TJI. And these are all bit messages. These are not probability messages. So they are either 0, 1, or in case of eraser channel, they may be erasers also. And what, okay, this is one part which was missing yesterday. Remember, I was saying that in my haste of preparing the slides, I forgot to draw this part. So in addition to the connection of a VN to all the CNs, VN is obviously also connected to the channel. And in case of binary eraser channel, the way we connect VN to the channel is if a particular bit is not erased, we just connect that value, that bit value, either 0 or 1. Or if it is erased, we say that value is X. So that is how we have defined B1, or in general, B of I. And initially, we will just have this B of I for each Vn of I. Subsequently, we start getting this B hat values, but initially B hat values are not present at the very first iteration. So the question is that when we have all this bit messages flowing in from the CNs and this bit message coming in from the channel, how do we calculate the message that the VN sends to the CN in the next iteration, or to be used in the next iteration? That is what is actually described here. But for this particular specific example, we can say that because VN is a repetition code, in case of binary eraser channel, if there are not erasers, then all of these values are going to be the same because it is a repetition. So, right, so all of this, 3 green arrows and then this B1, they all will have the same value, either 0 or 1. Or it could be that they all are erased. So if they are all erased, then we can't do anything. We would set BT plus 1, 1, 1 as an eraser. But otherwise, we will just set BT plus 1 to this common unerased value. For the sake of commonality, we can also use here majority voting. This is actually same as majority vote decoder, but here there is no minority. The minority has no member. But if you want to kind of reuse what you will be doing for hard decision over binary symmetric channel, you can implement majority vote, and that majority vote is same as taking any one of those bit values using that. Okay. Now remember I told you that there is okay. So by the way, yeah. So this is for binary eraser channel, and then for binary symmetric channel, we would just do majority voting because there are no erasers. So we will just implement the decoder of a repetition code, which is simply the majority vote decoder. So we would do majority voting on this 4 bits. And that majority vote is what we will send as this blue for doing that. Right? So that is how VN1 will send a message to CN1. Now, maybe I should also say that it's another diagram just for the sake of completeness. So I will draw the same diagram. I think instead of drawing, let me something else. Okay, so are you able to see the slide, by the way?
Yes, sir.
Yes, sir.
Okay, so what I wanted to show you is that when after VN1 sends message to CN1, remember we said that it has to send message to all the CNs. So after it is done with CN1, next time it will go to CN2, and so I will just move this blue arrow over here, and I will move this one over here. And I will put this one here, but now I will call it VN to CN. We call it actually CN. I3N to JCN. Okay, so first VN to the second CN. Okay, so I'll call it the message going from first VN to the second CN. That is the one that we have to calculate. That is this blue line. And now it is going to look at majority voting of this 4. Okay, so this is how the message gets passed from VN1 to CN2. And at this time, it will do majority voting over this green line, and then this purple line. Okay, so that is the idea. Then when it goes to the third CN, the blue line goes there and it does majority voting over 1, 2, 4, and B1. Okay, so this one I don't need anymore. I'll go to the next one. This we already looked at it. This is the simple change that we have to do for the binary symmetric channel. It's just majority vote on the 3 green arrows and 1 purple arrow, right? Now, see, this is the reason why I said that the 4 algorithms are actually there's not a lot of change. So going from the BEC hard decision to the BSC hard decision, look at what changed. See, this also is majority voting, but here also we are doing majority voting. The only change is that for BEC, we have to put this as condition that if all of them are erased, then we have to, if all of these values, the 3 green arrows and 1 purple arrow, if all of them are erased, then we have to send an eraser. Whereas for binary symmetric channel, there are no erasers, so we just do majority vote. So you see, it's a very simple change. And that changes only in the way we compute the message, not in the way we exchange the messages. And in this example, actually, that change is also, if you just write a function for majority voting, which also understands that there may be erasers present, then you can just have one function. Obviously, when all of them are erasers, the majority voting will be an eraser. So then this majority vote function can be just one function, and it will work for both BEC as well as BSC. So you would have kind of implemented 2 different decoding methods using essentially the same function. Now we are on step number 4. I think I made a mistake here again. So These step numbers are revised. Previously, I was calling them 2 and 3, but now because I added this initial step 1 here, they became 3 and 4. And so this should be step 3. Actually, this is 3.1, where we are just calculating the message. 3.2 we are going to look at. So this is all step 3. Specifically 3.1. And then now we are on step 4. And this slide also we have seen earlier. The main important part of this slide is that we never do positive cycle. Okay, and so that is why in this diagram, right, this blue arrow is never computed. The message on the blue arrow is never computed using the message that came down on the green arrow on the same line. Right. So when we were looking at the message to be sent to CN1, we ignored the green arrow that came from CN1 to VN1. Then when we went to CN2, we ignored the green arrow that came from CN2 to VN1. So that part is what is mentioned here, that we don't want to do this positive feedback, positive cycle. Now again, drawing the same type of diagram for a specific example where CN1 is connected to VN1, VN2, and VN3. The question is how we will calculate the message going from CN to the VN. And remember, this is also a bit message, except now this particular node is a Ldpc code. And so for binary eraser channel, what we will say is that if any one of these green arrows contains an eraser, then we can't do the modulo 2 sum, which is the Ldpc decoder. So this part is again typo. It is to be erased. So in this case, if either one of these two is an eraser for the binary eraser channel, then the check node says, I can't do anything. I have to send you an eraser. So if any one of these two are erased, then this value here b hat second. Yeah. So this b hat T11 has to be erased. Otherwise, it is going to be just the modulo 2 sum. So again, this is another typo here. This is T plus 1, it is just T. So this is the algorithm. Basically, CN to VN calculation, message calculation is based on just the single parity decoder, which is just modulo 2 sum. So now you can say that for the binary symmetric channel, again, because there are no erasers, it's actually simpler. You just do modulo 2 sum of the two incoming messages. So this is how you would do the Ldpc decoding at a CN. Then this is that step number 3.2. And at this time, we ask each VN to also provide us the decoded bit, the ith decoded bit of corresponding to that variable. And this goes out. This is our decoder output at the tth iteration. Now, you will notice that this is a new arrow that I have drawn, and it just output of the algorithm. Right? It is not forming any looping. We don't loop it back. We don't take this C1 at value at tth iteration and we kind of feed it back to the algorithm. This is just what we want to know as the decoder output. And so because there is no looping, there is no concern of positive feedback. And so we make use of all the information that we have, which is all the 4 green downcoming arrows and this purple upward arrows. So 3.2 is very similar to 3.1, except this first green arrow that was ignored is now included. So we just set C1t as the majority vote on all the 4 green incoming arrows as well as the channel output. This is step number 3.2. And then this is an example that we have already seen. Again, there is a mistake here. There should be this connection here. And this line should be erased. This is not the right line. Okay, but anyways, so this example I'm not going to go over because we already have done it before. I'm going to now directly look at the same algorithm for the soft decisions. And the reason why we need soft decision decoding is something we have already discussed earlier. So this slide also I'm skipping. So I'm now looking at soft decision decoding. This is a slide that we looked at yesterday, but I again have made a number of changes to it. Okay, so the parts that are different compared to the hard decision decoding are in color, in the purple, in the pink color. The black is same as what was there before. This is the same algorithmic description. And so you will see that there are a few changes. One is how we initialize the variable nodes. So that is one change, going from the hard decision to the soft decision. And then there will be changes in the way we compute the messages. So that will be the second change. And the third change is possibly in the way that we terminate the iterations. Okay. Now, one thing I will mention here is that yesterday I had made an error. If you recall, I had put a question mark on this step number 2, which I later on actually erased, and I said that no, there is no error. Then when I thought about it yesterday, during the day after the session yesterday, I realized that there was indeed an error. And so that part I have corrected now. So this part is correct now. The way we will load the variable node at iteration 0, at t equal to 0, for the soft decision decoding, is we will load it with probability, which is same as what I mentioned to you yesterday. But yesterday I said that this probability is same for all the VNs. But that is not the case. This probability that we will use at t equal to 0 is going to be the conditional probability that Vni is 1 given the received bit R of I. And so for the binary symmetric channel, this flip over probability is P. If we get R of I equal to 1, then what we will say is that the probability that that particular variable node is 1 is going to be 1 minus P. Otherwise, if R of I is 0, then P of I is going to be P. Now, this is a conditional probability. P of I is a conditional probability. Probability conditioned upon R of I. And R of I can take two values, and therefore this conditional probability also has two values. Why it turns out to be 1 minus P and P? So that is a calculation that we have done already. It is there in one of our earlier slides. So you can go and take a look at it. Or you can do this calculation on your own. And you will see that this is the right answer. Okay. Now, I'll take an example. Let's suppose P is very small. So suppose that P is like maybe 1%, 0.01. And now we ask that what is the conditional probability that V and I is 1 given that R of I is 1? Then what this answer will tell you is that P of I is going to be 0.99. And that makes sense because the flip over or the crossover probability is so tiny that whenever we get bit 1, we are we are like very highly confident. We are almost certain that that bit is 1. And therefore, we will give a very high value to P of I. On the other hand, so here it is, and if R of I is 1, then P of I is a very high number. On the other hand, if R of I is 0, then this conditional probability, we make it equal to P, which is 0.01, and that also makes sense. We got at the output of the channel, we got a 0. And we know that probability of flipping is only 0.01. And when we got a 0, we should give a value which is very small to the probability that this variable node is 1. And so that, again, is what you can see here happening. Okay, so that is how we will do the initialization. Either do 1 minus P or P, depending on whether we got 1 or 0. This is the slide that we had already looked at yesterday. The change that I made is over here. This part was missing yesterday. So this Vn has to be connected to the channel, and specifically in case of binary symmetric channel, by the way, this is for binary symmetric channel. We will also look at binary eraser channel later. The binary symmetric channel, the way we will do initialization or the way we will compute this P1 values is 1 minus P or P. Remember, this was different for the case of binary eraser channel. There, instead of P1, we had B1. And that B1 value was either 0, 1 or eraser. Now it's going to be a fractional number and it's going to be a probability. But, and similarly, these three green arrows now also will contain probabilities instead of zeros and ones. This is the same algorithm that we had looked at yesterday. Basically, we would do a product of the four numbers. Yesterday, this P1 was missing, which I have added here. Other than that, everything else is the same. So we can actually do this calculation in terms of likelihood ratios so that we don't have to specifically compute that normalization parameter. Or we can actually operate in the log likelihood domain, then we just add up these 4 individual log, log likelihood values. That way this should be held. This is the same diagram that we had studied yesterday. There is no change to it, absolutely no change. So I'm going to do this, flip over the slides. Well, okay. I take back what I said. There is one change. Yesterday, I think this normalization parameter was missing, which I have added here. But then here, there is no change. Okay, and then this is that step 3.2. This is how we will calculate the bit decision. And for, as we said, for bit decision, we will use all the 4 green arrows. So these are the 4 green arrows. 1, 2, 3, and 4. Then this is the channel part. So this will be the BSC output. So we will make use of all the information, again, to compute the likelihood ratio. Then once we know the likelihood ratio, we can estimate the bit. Who can tell me how do we estimate the bit given this value? Are you all asleep by now? Or I managed to put you to sleep?
No, sir.
Sir, if lambda greater than 1, then
Greater than
1
1.
Then 1.
Okay.
is 0.
Good. So that is how we will do the bit estimation. Okay. So that was for the binary symmetric channel. For the binary eraser channel, everything remains the same except the way we calculate P of I changes. Conditional probability that B and I is 1 given the received bit R of I. Now remember, for binary eraser channel, R of I can be 0, 1, or X. So this conditional probability we'll have to account for that. So who can tell me, and maybe I'll write it here, what is the conditional probability that the ith Vn is 1? So let me write it like this. P of I is equal to, and then there is this curly bracket, there is a blank, there is a blank, and there is a blank. This 3 blank is what I'm asking you to fill up. The first blank is if R of I is 1. The second is for if R of I is 0. And the third one is if R of I is an eraser.
Sir, 1 minus
1
P
minus
for
P
1 and 0, and for
Zero
eraser
and
it
P.
will be P.
Yes.
110.
Sorry, can you repeat again, Mudit?
1 for the first two.
So if you get R of I equal to 0 in the binary eraser channel, you will give the probability that the bit, the Vn is 1. You say that it is probability of 1 that it is 1, even though you got R of I 0.
Sir, 1, 0 and 0.
Very true. Who said that?
Sir, Devanshi.
Devanshi, you got it. I have noticed you now. Okay, by the way, I tell you this. It's partly because This is happening online, but partly also because a lot of you don't speak out. So I have noticed Vandan, okay, because Vandan speaks out a lot. I have noticed Harsh. Harsh also makes many good observations. Kandar, who else? Devanshi. These are the 4 people that I can think of right now. Out of a class of 340. By the way, out of 340, probably 100 or so don't even attend this lecture, but maybe about 200 plus of you that are attending. How come I know only 4 names so far? So that is not good. You have to speak out more. So if R of I is 1, the conditional probability becomes 1, obviously, because for binary zero channel, there are no flipovers. Bits don't get flipped. So if you get 1, then it has to be 1 that was transmitted. If you get 0, then there cannot be that event that the transmitter sent a 1. So P of I, which is the conditional probability that Bn of I is 1, becomes 0. You cannot have the transmitter sending 1 and you getting 0 in binary iterative channel. On the other hand, if you get an eraser, then you don't know whether 1 or 0 was transmitted. And assuming that the source prior is equal, meaning that Bernoulli Q variable of the source is such that Q is equal to 0.5, then now here you don't know, it probably becomes 0.5. So 1, 0, and 0.5. So this is the only change that we would make for the soft decision decoding of binary eraser channel. Everything else remains the same. Okay, so we have maybe about 20 or 25 minutes more. I'll take a very quick break at this point, and we will now look at, in the remaining time, we will look at the before we move on to the Ldpc code, I again want to reiterate that these 4 different decoders, it's like almost like when you are moving into a new house and you are furnishing and interior decorating your house, and you got a lot of furniture and you get a lot of decorative items. I think that main work is in doing that. Then going from one decoder to another, it is like just moving a photo frame from one wall to the other. Okay, it's comparatively much smaller effort. So that is how you should feel it when you are doing the programming. So I suggest that as a part of team, when you work, you probably want to allocate more resource. More of your team members should be working on developing the Ternary Graph part of the algorithm, maybe even the Monte Carlo. And then maybe only one person can look at this different decoder types, or maybe you can have 2 people looking at it. So that is one thing that I want to do. Don't worry too much about how will we implement 4 different decoders. The main focus should be on implementing the Ternary Graph structures and the iterative part. Then changing from one decoder to another is going to be not that much of an effort. I mean, it will be still some work. You will have to still do sanity checks, and you will have to verify your algorithm for each of these 4 cases. And there again, I would suggest that the way you would verify is first you disable the noise. There is no noise. This probability P of BSC or BEC, you make it 0. And then you make sure that your decoder is able to recover the actual code word. If it is failing there, then you know something basic is wrong. Okay, so that is one thing. The other is that suppose you are working on implementing the soft decision decoder for binary symmetric channel. then what I suggest is you don't keep your vision to be narrow. You don't say that I'm going to only look at implementing the equation for the SDD of BSC. You should also look and fully understand the rest of the code of which does the message passing. And also maybe the Monte Carlo part, maybe how you are calculating the probability of successful decoding and all that. So it's always good to look at the code that you yourself have not written, but which you may become owner of. That is what happens in your future workplace. Maybe you will have developed only a part of a big program, but then the other people who would have written other parts, they may move to a different department, or they may leave the company, join a new workplace, and then you end up being the owner of the whole thing. And at that time, your manager or your vice president is not going to say that, oh, it's okay if you don't tell me why this software is not working because part of it was not written by you. They will say that you are the owner, you have to make it work. So take that ownership. Okay, now moving forward. So what we should have noticed by now is that the main complexity of the decoder, which is in terms of mathematical calculations, depends on the DC and DV. Because all the calculations that we did, either majority voting or the modulo 2 sum for the hard decision, or all of those log likelihood values and all that, there, the number of multipliers, the number of divisions, and so on that we were doing were limited by DC or DV, depending on whether we do calculation at the check node or the variable. Now, it is known for a long time, and this also is kind of connected to that notion of typical set, right, that we had studied earlier. The typical set gets realized only when the length becomes very large. And so based on that thinking, it was known for a long time that in order for the coding scheme to work very well, we should have a very long code. This we know also through the repetition code. Also, although it's a very simple code, we have seen that if I want to get a probability of error of 10 to the power minus 15, we need the length to be about 63 bits. Very long code. In fact, today, the Ldpc codes are easily 1,000-bit long or 2,000-bit long. And in some initial studies, people had designed and developed the algorithms for Ldpc codes that were 64,000-bit long. Right? So this is an important thing. We need to make a code which is very long. But if we make the code very long, and then at the same time we keep on increasing the number of edges of each VN and each CN, then the decoder will start becoming computationally intensive. And so ideally, what we want is a code which is very long, which means that capital N tends to infinity. But still, this DC and DV are small, maybe less than 10. So that is kind of the overall requirement. Now, if I construct a code and look at its parity check matrix, what will it look like? Who can tell me?
Sir, most of the portion will be 0 and very few places it would be 1.
Correct. So that is the right answer, Harsh. You have studied in your physics how an atom looks like. Some analogy is given that the atom is, if you think of it as like a football field, then the nucleus is just like a football at the center of the field, and the electrons are some dust particles, few of them. So most of the atom is actually empty. So if you look at the parity check matrix of this code having this desirable property, it is going to be a huge parity check matrix, because remember the size of the parity check matrix is U cross N. And as N becomes big, the parity check matrix starts becoming big. But because each row and each column has only few ones, most of the parity check matrix is going to be zeros. So that is where the name low density comes. This is not density in the sense of the way that in physics you measure density of something, but basically it looks empty. And it's a parity check matrix, so that's why it's called low density parity check. And low density is sometimes also written as a sparse matrix. Basically, the number of ones is sparse. And the row and the column weights are independent of the length. And so therefore, the decoder complexity doesn't grow even if you make N to be large. Now, the Ldpc codes were developed by a scientist called Robert Gallagher in his 1960 dissertation. And I would put Gallagher's paper almost in the same category as Shannon's paper. Shannon came up with the problem and he said what will be the optimal solution, how it will look like. That is his channel capacity formulation that we have studied earlier, that information transfer formulation. But his paper didn't say how you can achieve that. Right? We saw earlier that if you just try a repetition code, it falls far short of the channel capacity. How can we actually get to the channel capacity while keeping the decoder complexity manageable? There were some proposals which theoretically could achieve channel capacity, but then the decoder complexity will just be too bad. It will just blow apart. Even today's processor cannot implement those decoding schemes. So Gallagher's paper, by the way, which I have written, which I have read a number of times, is such a nice paper that it solved this problem entirely, and it gave all the detailed way in which this problem can be solved. A very thoughtful paper, very, very nice paper. It is brimming with ideas. But unfortunately, in 1960, the processors were still so weak, they were so puny, they were so tiny that even this low complexity LDPC decoder was too much to implement. In those days, people can do SPC decoding or repetition decoding, and that too for small values of N in the processors that were there at that time. But what Gallagher said is that, first of all, I need N to be pretty large for this codes to be working very well. And as N grows, although DC and DV he made purposefully to be small, maybe 3 and 6 and the values like that, you still have to visit each of these N VNs, right? Each of the N columns of the H matrix. And so if N is 10,000, then you have to go to each of these 10,000 columns one by one. And that was just simply too much for the processors of those days. So he proposed it in 1960, 1961, 1962. Those few years, these Ldpc codes were discussed, but then everybody forgot about it because they said, okay, we can't do it actually in the implementation. And happily enough, this Gallagher person also forgot about it. So he then went on to some other activities. Actually, then he wrote a nice book on computer networks. Bert Sekas and Gallagher. If you look up computer network book by Bert Sekas and Gallagher, you will easily find it on Google or Amazon. And when you take this computer network course later on, you can refer to his book. It's also a nicely written book. So he went on to do all the upper layer parts of digital communication, right? The ones that we have briefly talked about, the data link layer, the transport layer, the IP layer, and so on. But the problem of realizing channel capacity through manageable complexity codes was not forgotten. People kept on working on that problem. And then in mid-1990s, these two researchers, David McKay and I think it is Robert Neal, they rediscovered the Ldpc codes. In fact, they must have had a disappointment because they actually came up with the same idea on their own. And so they thought, oh, wow, we will be very famous. Well, they are famous, but still their name is not mentioned in the Ldpc code. Ldpc codes are associated with Gallagher because their invention turned out to be same as the Ldpc code. And then after they did it, they realized that, okay, what we have done is just repeat of what Gallagher already did 30 years back. So all the credit should be due to McKay and Neal to bring Gallagher code back into the foray. But the name that is associated is the name that Gallagher gave, which is the low density parity check. Okay. And now Ldpc codes are everywhere, not only in 5G. When I talk to ISRO, they are very much interested in implementing Ldpc codes on their satellite links. There are some deep space missions. Their Ldpc codes are being considered. There are some satellite to satellite, inter-satellite links, which are all in the sky. The signal never goes to the Earth. People are talking about putting Ldpc codes there. The fiber optic communication, your and now Geo Fiber is there, and there are many other fiber providers. So the fiber modems, people are talking about using Ldpc codes over there. So Ldpc codes are like wildfire. They have spread like wildfire. Everybody's talking about Ldpc codes these days. By the way, there is another nice coding scheme which is called turbo codes, which we are not going to study in this course. But they also are very efficient. They also approach the channel capacity. And they are also based on some really smart ideas. And it turns out that the decoding of turbo code also is happening in terms of message passing and belief propagation. And so that is where this entire scheme of belief propagation got a lot of attention and attraction about, I would say, 25 years back, maybe even before you were born. And that interest is still there. A lot of people are still working on this belief propagation type of algorithms. So what is an Ldpc code? This we have already talked about. This is one example from McKay and Neal's paper. This is a very small code. It's not, capital N is not very large. I think capital N is only 12 here. There are 12 columns. And this is a rate 0.75 code. And the reason is because the number of parity checks is 9. So you'll see that there are 9 rows. So capital U is 9. Which means that out of 12 encoded bits, 9 are actually coded bits. And so, so actually the rate is only 1/4. Right? Out of 12 information bits, only k equal to 3 bits are information bits. The remaining 9 bits are parity, and so the total n is 12. So this is rate 1/4 code. So as you may have noticed, as the rate decreases, the number of rows of H increases. The number of rows can never become same as the number of columns because then the rate will become 1. The number of rows is always smaller. And if the rate is very high, the number of rows will become smaller and smaller. And then the rate becomes greater and greater. In the limit that the number of rows is just 1, then the rate becomes n minus 1 divided by n. But that type of LDPC code is useless. It doesn't work very well. What people now believe is that you need the degree of the variable nodes to be at least about 3. So you will see here that the weight of each column, which is the dv, by the way, we can also call it wc. So you know wc and dv are the same. Weight of each column is 3, meaning the degree of a variable node is 3. And weight of each row is 4. Degree of a check node is 4. This is called a regular code because all the check nodes have the same degree of 3. All the variable nodes have the same degree of 4. There is a regularity in the H matrix. Today now, a lot of the H matrices that are used are irregular, meaning the degrees can be different going from one variable node to the other. So in your project, I will ask you to do first the LDPC decoding for this H matrix. And then once you have successfully implemented the decoder for this H matrix, which will not work very well, by the way, because n is very small. But at least when the noise is very low, it will work. In fact, its performance should be maybe better than the Hamming code, because Hamming code n is only 7. Its performance should be also better than the rectangular parity check code, whose n is 14. The other thing that you might have noticed is that the arrangement of ones is kind of ad hoc. It is random. Ideally, what people realize is that you make H to be actually an all-zero matrix. It should be filled up with zeros. U cross n zeros. And then you just randomly throw darts. And wherever the dart lands, you put a 1 there. That is what people think is the best way to define an H matrix. But truly random throwing of the darts is not feasible algorithmically, and so there are some algorithms that are now developed which come up with how to populate ones when this H matrix becomes very big. Ultimately, when you look at it, it seems like you put ones in an almost random manner. So after you solve the problem for this small h, then extending your program to a larger h is no work. You just let your program run for n, which is bigger. So I will be giving you maybe 1 or 2 h matrices which are going to be bigger. Maybe they will have n equal to 5,000. And then you will have to just rerun your algorithm, your Monte Carlo simulation on that large H matrix. Okay, so this is where we will stop today. If you have